Okay, let's get started. So welcome everyone to another lecture in our ID 5130 parallel scientific computing course. So let us continue our discussion on MPI derived data types that we started yesterday. Okay. Fine. So essentially, we were kind of referring to essentially our trapezoidal rule program as a motivation to look at derived data types, in which we, if you recall, we have in the trapezoidal rule, we have to, if you read the values of a, b, and n, which is the basically the left and the right values of the integration, and this is basically the number of trapezoids, right? If you read these values from the user on process 0, then what we had to do was, if you have to make this available, of course you have to make it available to all other processes, because this is kind of a global data that is required by all processes. Okay, so and if we have to do that, we either have to use an MPI broadcast 3 times for each of these values, or we had to use MPI kind of send and receive calls 3 times for each of these values. Okay, so this is basically just an example problem, but in reality you might actually work with exchanging the data or several data many times during your program, right? In different iterations and things like that. So that is kind of the motivation. However, in this particular example, it really doesn't probably save much of a time, unless, I mean, other than just saving 2 calls as such. But the big picture is that we may end up doing something like this for every iteration, which might be time consuming, and that is where we would use the derived data types. Okay, so so instead of sending these 3 variables in 3 different messages, we could actually save time if we could just send basically one message, which basically consists of 2 floating point or double values plus 1 integer value, and all of them together, right? So essentially we would like to and such a combination would be a new data type, right, that we want to define, and that is basically similar to what we would have in a in C as a structure, right? If you define using the struct argument keyword, right? So we would like to do that in MPI, so that MPI would basically be able to send all of these in one go, right? So MPI should basically know what is the what are the data types that we are sending, right? Because this would basically inform MPI about number of bytes it has to read in the particular memory location, and it also should know where they are where they are available, right? That means it should also know what is the so essentially it should know with respect to with respect to the first arguments, where are the other elements that we are sending located, right? So it basically would like to know what is the difference, or what is the displacement between the second argument and the first argument in terms of number of bytes, and then similarly what is the displacement of the third argument and the first argument. So everything will be with respect to the first argument is what it is. So for example, let's say we have the variables and some address in the memory location. Let us say a variable a, b, and n have some memory locations here. Let's say it has 24, 40, and 48 are the addresses in the memory. Then for example, what MPI would require is, it would require it would basically require a data that is basically to derive a new data type. It would require something like this. It would require MPI double and then 0. Basically tells you that this is, you don't have to offset anything from the first argument, and then the second argument is again an MPI double, because this is B, right? And then the second argument is offset with respect to the first one by 16 bytes or whatever, right? And then the third argument is MPI int, right? And it is offset from the first argument only by 24, right? So essentially you give 24 here. So this is what MPI requires in order to kind of map all these values and then send all of them in once, and then when it is received on the other side, it should also be able to put them in a similar way, right? So that is what it is. Now of course we don't know what these memory locations are unless we basically inquire them, right? So we would see how to basically get these on every process without actually worrying about what exactly the values are by using some function. Okay, all right. So the first argument, of course, is basically here is the data type that we are sending. So this is the data type of A, B, and N. And the second argument is the basically the displacement of the argument with respect to or relative to the first argument. Okay, and this is in basically given in terms of bytes. Okay, all right. So what we would use is we would use a function to in order to define a new data type. We will use a function in MPI that is known as MPI type create struct. So just like other functions, it has a return type of integer, and then we have MPI type create struct. So you will notice that only the T and is capital here and everything else is lowercase, and then it would take in basically the count. Okay, it would have a count, so basically how many variables are we sending, and then it would also require an array of basically block lengths array. So that means we will come to this, and then it also has a new data type that is basically MPI A int. Okay, and that is basically the we would have the displacements, which would be given in terms of the number of bytes. Okay, and then we have the MPI data type. Okay, so we would have again an array of the data types of the values that we are sending. Okay, so this is the type. So for example, this basically types would contain MPI double, and MPI integer here. Okay, all right. And then finally we would have to also pass in the address of the or basically a pointer to the new variable that we are creating. Okay, we are creating a new type pointer. Okay, that's what it is. Okay, so basically it takes in 5 arguments. We will see what these are one by one, and the last argument here is the out argument. Everything else is basically an input. Okay, so here the first argument count basically tells the MPI that essentially it basically tells how many values need to be passed, right? So in our present case it is basically 3 because it is A, B, and N. Okay, and then we have an array here. The array is basically contains block lengths. Now block lengths allows it for these variables is basically an array. So block lengths basically makes an allowance for the variables to be arrays. So if you want to pass arrays, then block lengths of each of the block lengths would basically contain a number that indicates how many array elements are there in the first variable. For example, let's say if the first argument A, instead of being A, if it A of 5, then we would write it like this, right? We would fill block lengths of 0 as 5. So basically that means the first argument, which is A, which is indicated by 0, has 5 elements. But in this particular case we are just sending one real value, so basically block length of 0 is 1, and of course 1 and 2 is also 1 and 1, right? So essentially it can be initialized to 1 everywhere because we are sending 3 values, not arrays anywhere. Okay, so that's what your block length indicates. And then the next argument is the displacements. Now displacements is something that is important. So displacements array contains what is the offset, right, of the argument with respect to the first argument. Okay. Now, of course, we do not know very we do not know this value, so we have to kind of use a different function and then kind of probe for it to know what is the address. So for this we will be using to find these values of displacements. For example, in this particular case, as we looked at in the example, displacements of 3, right, the 3 displacements could be equal to 0, 16 and 24, right? Excuse me, like what we have from this example. Okay, now of course this is just a for the sake of example. Now in reality what we would do is you would call this function essentially int MPI get address, that is provided by MPI, and then it takes in 2 arguments. The first one is the variable, right, a pointer to the variable, and the second one is the MPI a int star. It basically gives you the pointer to the address. Okay, now you may be wondering, so this is basically the input and this is the output. Okay, output argument. Now what is this new MPI a int that we have been using? So MPI a int is basically is an integer, that is an integer type that is defined by MPI, which will basically allow MPI to hold addresses in integer format. So that means this integer will be like a very long integer, such that it can basically use any address memory location. It can represent any address memory location using an integer here. Okay, so usually the addresses are represented in hexadecimal, but then here it will be using just a integer value, okay, to store that. All right, so so that basically once we do this thing, we can basically fill in the displacements values by calling MPI get address maybe 3 times, right? Basically we just have to call, so that means we need to of course first declare to get these addresses, we need to declare a variable. So we will declare a variable using MPI a int. We would say a address, right, and then b address, and then n address. So these 3 variables would basically hold the addresses once we call the MPI get address, and then we're going to call MPI get address, and we are going to pass in the a, and then going to get a address, right? So this will also be a pointer because both are pointers here, and then you would again call MPI get address ampersand b address. Okay, and then similarly you would pass in ampersand n address. So with this we will get the addresses in a, b and n. Then of course we can fill in the displacement. So displacement of 0 of course is 0 because you will pass in the a as the first argument. So the displacement of a with respect to itself is 0, and then in the displacement array that we have to pass to the type create struct. So this first one would be basically you would subtract a from b. So basically b address minus a address will give you the displacement for b, and then similarly the displacement for n, that is basically your third argument, that is your 2, is c address minus a address. Okay, so using this these 3 lines we can fill in the values. Now it may get, as you can see, it may get cumbersome if you have a lot of values. Okay, but yeah, it is kind of required to do this so that we will save time in the MPI send and receives. There are also other ways of sending data if your data happens to be contiguous or it has some pattern that we will see towards the after finishing the discussion on the MPI derived data types. Okay, all right, so this is how you would fill in. Then of course you have what are the other arguments remaining. The other arguments are we are done with the block length, displacements are done. Next is the type, right? So we need to look at types. Okay, so types is basically contains MPI double and int. Okay, so I just have to write here your types array of 3 would basically contain the MPI data type. So this is basically your MPI double, right, and MPI integer, right? That's what it is. Then so basically you would define types as MPI data type, right? You would define MPI data types as 3 types of types of 3 equals MPI double, and MPI int. Okay, so that's what we would do. It should be capital, otherwise it will give an error in C. Okay, so now that we have all these values with these initializations, we can now actually start defining a new data type. So for that we basically have to first declare a new variable. So that is MPI data type. Let us say we will declare something like MPI a new type. Okay, so we declare a variable, so that variable, and then we would call in MPI type create struct, right? Type create structure, right? And then you would send in the count as 3, and then the block length array, as we have already filled this. So you send in block lengths, and then you send in displacements, right? And then you send in the types, all these arrays which we have filled above, right? And then you have, of course, the new variable that you want to do, that is basically MPI new type, right? So that is the new type, which is basically will be pointing to those 3 values. Okay, now before we can directly use this MPI new type, we first have to commit it to MPI, so that MPI can do some kind of bookkeeping, and then it would kind of register that new type in its own internal memory, so that the next function call would basically tell that, okay, this new value is basically new variable is being used. Okay, so for that you first have to call the MPI type commit. Okay, MPI type commit, and then you basically would say MPI, you send in the corresponding pointer star, and then you would just put in here MPI new type pointer. Okay, so which will basically work as both input and output, because that will be registered by MPI, and then the registered one will be kind of sent out again. Okay, all right, so so far so good. Then of course, once we have this thing, we can replace all the 3 calls to MPI broadcast or MPI send receive by just one function call. And how do you do that? You basically call MPI broadcast, right? And then you send in the first argument, that is A, and then you are sending in only one value of type, the new type, that is basically MPI new type. Of course, you have to put in an ampersand there, and then broadcasting from process 0, and then you put in the communicator. Okay, so that is how you would call in. So now you can use this as any other, just like any other type, MPI, let's say MPI int or MPI double, right? You can use this new type that you have now just committed. Okay, so that can be used. All right, so that is essentially how you can basically define new or derived data types and use them. Okay, all right, so there is also other derived data types that basically use or can be defined based on contiguous memory of contiguous data that is in the memory, or using a vector kind of data type as well. So we will come to that. So before that, let us take a look at an example program which is basically the trapezoidal rule with all these changes that we have discussed till now. Okay, so what I did was I started off with the MPI, the trapezoidal rule program that we have seen before, and then from the version 1 I made all these changes, and then I ended up with this program. This is basically program MPI trapezoidal v2.c. okay, so that's what I have kind of came up with. So let us kind of see what we have here. Okay, so MPI parallel version of trapezoidal rule that makes use of derived data types. Okay. All right. So then, I mean, we basically have these include header files. Then we define the pipe, but we don't actually need it because now I am going to read this from the user. Okay, and then this function is the same as before. Then we have our trapezoidal rule, which is again same as this before. Then okay, now I basically have this new function. This I call it as MPI. So create new MPI type. Okay, so create new MPI type is taking in the pointers for the three variables, that is A, B, and N. Okay, and it is also taking in the new type that it has to create, which I call it as new MPI type pointer. Okay, now this function I have filled in the block lengths to be 3 because we have A, B, and C. All three are just integers or doubles, so they are just single values, they are not arrays. And then the types, which is basically has MPI data type types. Again, I fill in as MPI double, and MPI integer. Then I have MPI an integer for address. So this is basically address integer. Okay, so this stands for A stands for address integer. Okay, an integer for storing the addresses. So of that type, I basically define an address for A, B, and N. Okay, and then finally we have the displacements, for which I also have MPI in displacements contains 3 that also is initialized to 0, 0, 0. Okay, then first thing I would call is, of course, A, B, and N are already pointers, but then their address is already allocated. These variables are already there, and these variables will be picked up correspondingly on the corresponding process. Okay, so this is where, so the addresses will be corresponding to each process, so we don't have to worry about it, right? This question might have popped up in your head that what about other process. So automatically this will be taken care, because once the new MPI type has been arrived on the new on any other process, it should know the correct address where it should put it. Okay, so that will be taken care by this automatically, so by calling this function. So basically you are passing in, you're calling MPI get address, and then passing in a pointer to A, and then A address is what you are asking it to update it to, right? So you get A address, B address, and N address in these variables. Then displacements of 1, you would say B address minus A address, and then displacement of 2, you would say N address minus A address. Okay, that basically fills in the offset with respect to the first argument. Okay. Okay, similarly here also it is offset with respect to the first argument. Okay, then we have to now create the new MPI structure. So I would say I would call this function MPI type create struct. We are creating a structure with 3 elements, and then block lengths we are passing in, which we have already filled to be block lengths already filled to be 1, 1, 1. Displacements also filled to be whatever the values, 0 and something and something that was given by MPI get address, and then types is already filled in to be double, double, and int. And then we pass a new MPI type pointer. This is already a pointer, so I don't have to pass the address. All right, then we have before we use the MPI type, we need to commit it. So I'd say MPI type commit new MPI type pointer. Okay, so that is the creation of the new type, and then this created new type. Okay, then I have another function which basically is read user input. It takes in the process rank, number of process that in the communicator, and then it also takes in A, B, and N values, which it should read from process 0. So I define a new MPI type here, and then that is what is created in this function, right, which we just saw. Okay, basically declare the variable here, and then in this function call we have created it and then committed to MPI, so it is already available. Then if my ID is equal to 0, I would basically read the values on process 0. This is basically just to help us do this exercise. Then you broadcast the values to all the process using, instead of sending 3 values, you use the A pointer and then 1 and then new MPI type, and then this is being sent from 0 and then using MPI communicate word. Okay, so that basically already sends in. Then we have to also remember to free the MPI type free, because it is no longer required. Okay, because what happens is when you create a new type, MPI would allocate some storage to do the bookkeeping and things like that, so that needs to be freed if you don't need it anymore. In this particular case, I don't need it afterwards, but if a particular for any other function, if you need it multiple times, you don't have to free it here. You could free it before you call the MPI finalize. Okay, then basically free any memory that MPI has allocated, while creating a new derived data type. Okay. Alright, so that's what we have. Then of course my main function is now, main program is very straightforward. So what I did is I commented out the values of n, a and b because I would like to read it from the user, and then instead I call this function read user input, and then I send in my ID, number of process, and then I send addresses for a, b and n, which needs to be read from the user and then send it to the all process. Then everything else here is the same as the version 1. Okay, is the same as version 1. Okay. Fine. So let us see if we can run this program and if we still get the correct answer. So I would say okay, MPI CC, MPI program, MPI result v2.c minus link with math because we have a signed function, MPI run minus NP, let's say 4 processes, a.out on my own laptop. Okay, enter the values for A is the lower limit, that is 0.0, 0.0, B is the upper limit, I would say 3.14159, and I would like to take, let's say 1024. Okay, okay, that has printed that the area under the curve 1 plus sin x between 0 to pi is equal to, okay, this needs to be changed because I could change the limits pretty much to whatever I want in the input here, is equal to 5.14158 something, seems to be correct. Okay, we could probably experiment with maybe 2 processes as well, and then just to verify 0.0 and then 3.14159, and then let me use 1000 values. Okay, seems to be fine. Here also get the same answer. Alright, so it seems to be working fine. So this is the program which makes use of the new MPI derived data type. Now you could do very similar thing in FORTRAN as well. I'm not covering in the interest of time, but you can do pretty much the same function calls with all capitals or all lowercase, and then with the additional arguments such as MPI error at as the last argument, because in FORTRAN you don't have a return value for the subroutines. Okay, fine. So so that is about the MPI derived data types. So let me move on to couple of other useful data structures that are there in MPI, which will be much more useful to you when you're trying to write your own codes in your research. Okay, so the other derived data types, derived data types in MPI. So I'm going to talk about a couple of them. The first one is the contiguous data or continuous data. Okay, that's so continuous data type. The another one is known as the vector data type. Okay, now the continuous data and the vector type of these might be very useful. We will see how they are useful using an example. Okay, so the contiguous data, as the name suggests, basically you are referring to a consecutive or memory locations, right? Basically you have a continuous memory locations. Now at first thought this may look like, why do I actually need this thing, right? Continuous memory locations, because you might think I can just put in some number or the length of the array and then that is anyway in a continuous memory. So why would I actually need this thing? We will see. And then the vector data type is basically where you basically have a particular pattern of values in memory, right, of memory that you want to exchange. Okay, fine. Alright, so let's first look at the continuous data, which is very straightforward. So the function is basically int MPI type, and then in lowercase you have contiguous. Okay, and then the arguments are very simple, int count, that is basically how many contiguous values are there, and then the you would have 2 data types. One is MPI data type, that is the old one, right? So old type. So for example, let's say you're creating a new data type out of 10 integers, this would be MPI integer, right? And then you would have the new data type that you want to call with a different name, so that is star new type. Okay, so the new type, now let us say if you give in 1000 elements and then you give in MPI integer, right, then that's going to create a new type with whatever name you give, and that itself will be one type of that will already contain 1000. So when you exchange, you just have to use 1 to exchange 1000 elements, okay, in this new data type, like what we have done in the structure that we have seen just now. Okay, all right, then how would you, so in FORTRAN you basically have the same function call. You basically have MPI type contiguous, okay, and then you basically send in count old type and new type, okay, which is very, very similar to what we have now. Okay, coming to the usefulness. So why do I actually need this thing? So when you come to usefulness, the first thing is it may make your code clean and easy to understand, right? But that is not a real kind of purpose. The other purpose is basically this particular data type, contiguous data type, may be used as an intermediate data type when you try to build more complex data types, okay. So let us say you are building a particular more complicated data type which has a particular pattern of memory, okay, and then in that you know that particular pattern of memory may not be represented using may not be represented easily using just a vector or with a contiguous or with a structure, okay. Rather you may have to make use of vector plus contiguous to basically define so basically then in what you do is you define a new variable, new type for contiguous, and then use that new type of contiguous for the vector to basically come up with another new type, okay, and then that final new type is what you would use, okay. So basically you will have a contiguous type, and then you would use contiguous type, so you will use, let's say, MPI int while deriving contiguous type, and then you would use contiguous type to derive another vector type, something like this, and then this vector type is what you will finally use to exchange data, okay. So in such context, and this is very much is true because this is already tested. I mean we also use it very much, and I think when you try to write your programs, when you try to do the project as well, you would probably use something similar depending on the project you will work with, okay. So that is when the contiguous memory data type will be useful to create a new data type, okay. All right, so let us look at the other one, that is the vector data type. Vector data type is very important. Let us say for some reason we don't want to pass continuous data, but then we have an array, okay, and we would like to pass certain elements of this array, and those elements have a pattern, okay. Okay, we will see in which context we will basically get this kind of thing, but before that let us assume that we have an old data type. So this is the old type. The old type could be basically your MPI int or MPI double or something like this, and I would represent using maybe a block like this. So this kind of represents a block in memory that has maybe a few bytes, okay. This basically occupies some bytes, and then this is one block of memory. That means this is one variable. So this is, let's say, variable A, or this is variable A of 0, okay. So an A is basically an array with 0 to n minus 1. So one element is this is basically is like this. Now I would like to define a new type, okay, and then that new type is basically has a pattern, and that pattern is what I would draw here, okay. Let's say I have approximately like this, then let's say I would draw in values, okay. So it's basically each of them is a new it basically is a repeat of this block, okay, is what I have drawn here. So I have 1 2 3 4 5 6 7, okay. We make more boxes. I'll just draw it here, okay. 8 9 and This is easy. Okay, fine. So we have 10 of these things. So what I would like to do is the new type I would like to do, let's say I want to send basically these three, and then I have a gap of 2, and then I have, let's say, these three, and then I have a gap of 2. Okay, so this is how it is represented. Let's say this is a this is the array A of n, okay, where n equals 10. So we have 0 to 9 values here, and then I would like to send in only the 0, 1, 2, and then 3, 4, and then 5, 6, 7. Only these cells that are shown in red is what I want to send. Okay, so for this MPI allows you to do such patterns with MPI vector type. In MPI's terminology, what we have is we have to introduce a few words here, and those words is what MPI will use when you create a vector type. And those are the first one is the count. So how much is the count, and the other one is the block length. Okay, then the other one is the stride. Okay, so in this case block length is basically equals 3, because this is one block and this is another block. Okay, so this is the block length. Okay, so block length is 3 in our case, so there should be some kind of a repeating pattern. And then count is, we have basically how many of such blocks? 2 blocks, so we basically have a count of 2. And then what is the stride? Stride is the distance between the first element of the first block and the first element of the second block. That means how these are separated. So the stride is basically 1, 2, 3, 4, 5. So the stride is 5. Okay, all right. So so that is how kind of MPI allows us to define the patterns in memory, so that we can send in using a new vector type only these values without actually having to create a new structure or using the create structure commands. Okay, so this will basically allow us to define new MPI data type, and with that data type we can actually send in all these values in one go. Okay, fine. Now you might be thinking, where would such a pattern be useful? That basically has some values as blocks, and then there are also some gaps, right? So where will such memory patterns are useful or needed, right? I mean, essentially, when we say memory patterns are needed, we are saying that where will there be a need where I have to send in these kind of patterns across processes, right? Across processes, right? Now the idea is you will easily find them in your essentially in your let's say if you try to write your Jacobi or Gauss-Seidel in a 2D on a 2D domain, on a two-dimensional domain, you would basically end up with some patterns which you have to send exchange across the process. Also it is also possible that if you are working with, let's say, 2D or 3D domains, then you may have to extract a sub array, of the total array which needs to be sent. So in such circumstances, you will be using the vector data type to define and then commit a new data type, and then you can start using it. Fine. All right, so let us see the nitty-gritty of this. How does it work? So how do we represent 2D arrays in C or FORTRAN, right? So basically representing two-dimensional arrays in C. Okay, let's start with C first, and then we'll come to FORTRAN next. Okay, let's start with C first, because otherwise it will mix up, because the way of representing arrays, especially in memory, is different between C and FORTRAN, unfortunately, adding more things to what we should learn. Okay, so let us say in C you have a two-dimensional array. You have x of I and j. Okay, so we have the first index is I, the second index is j, and then let us say this is basically a 4x4 matrix. You basically have x of 4x4. Then how does let us say I would represent I as the horizontal here, j as the vertical here, and then I start off with from the bottom. Let's say in C we are talking about only C for the moment. So let's say x 0 0 is stored here. Okay, then as I go in the I direction, I increase the first index, that is I, x1 0, right, and then I increase x2 0, and then I say x3 0. Okay, similarly, as I go in the Y direction, I would increase the second index, that is 0 1, in the Z direction 0 2, and then I would say x of 0 3. Okay, this should be 0. Okay, similarly we go here, it is x1 1, and then you can fill all these things, and then here it will be x3 3. Okay, of course we have kind of allocated a two-dimensional array. However, whether it is any n-dimensional array, it doesn't really matter to the compiler and to the memory. All of these basically will be a continuous set of data, right? Continuous set of memory locations, and that is how it is allocated in the memory, right? So basically this is going to be represented as, you have, let's say, 16 elements. You have like 0 0 to 3 3, so it will be 1 2 3 4 all the way to, you would have all the 16 elements. That is how it will be stored in the memory of your computer, right? Now of course, what does 1 2 3 4, you know, what does 3 corresponds to here, where would it correspond? That is what distinguishes the memory pattern. And in C, basically C uses something that is known as the row major ordering, or also known as lexicographic ordering. Okay, in which the memory is stored with a row majority, right, row major order. And how is that represented? So if I were to draw this 16 memory locations here with a correspondence to these locations, if I map these 1 to 16 in this matrix form, so then what I basically have is, what C does is it will go in the row major order. So it basically goes in the rows first, then it will come to the next column. So it will go start from 1 2 3 4, then it will come to 5 here, right? So what we have is, you have 1 2 3 4, you have 5 6 7 8 9 10 11 12, and then 13 14 15 16. Okay, that is how it will store. That means essentially you are, if you want to refer to 5, you basically have to refer to this memory location, right? Or if you have to refer to x10, which is basically 5, right? So that is how the memory is done is allocated in C. Okay, now okay, this is fine, but how would it actually affect us? Because it will affect us when you try to extract different elements. We would not know what pattern it is. Basically, will it refer to, you know, when you say 3, would it refer to 2 0 or 0 2? Okay, that is important, unless you are working with a symmetric matrix, which you will not be many a times. So let us say we would consider a let's say to kind of demonstrate this, consider a 5 by 4 matrix, and we want to extract let's say 3 by 2 sub array out of this matrix. Okay, and using C. All right, so let me draw a 5 by 4 matrix here. Okay, 1 2 3 4. Okay, and then I want to draw 2 3 4 5. Okay, so basically I have 5 rows and 4 columns. Okay, and I want to extract a particular, let's say 3 by 2 cells here from here. Okay, so I want to extract these cells. These are my 3 rows and 2 columns. I want to extract these this particular 3 by 2 cells from this 5 by 4 matrix. Okay, and now so this is a 5 by 4 and this is your 3 by 2 cells, right? Okay, all right. Now first of all, how is this now represented in memory? If I were to draw this, then let me draw. So basically I have 20 elements, and then as you have already seen, this is done in row major order. So the memory would basically contain basically it will contain 1 2 3 4 5 columns, right? So the first column, second column, third column, fourth column, and the fifth column, right? And in each of the columns we basically have 4 elements. So 1 2 3 4, 1 2 3 4, and then you have 1 2 3 4, 1 2 3 4, and then 1 2 3 4. So that's basically makes up your 20 elements. Now where will these reds go? So the first one doesn't have any reds, the second one has reds, right? So basically that is the one. Basically it starts with the second to third. So you have, this is the data you want to send, and then the third one also has the value. So basically you want to send these values, then you want to send these values. That's all, right? Okay, very good. Now now can you tell me what is the can we look at what is the count, block length, and stride? So let us say block length. Oops. Okay, so what is the block length? Okay, let us start with the block length, then count, then stride. Okay, the order in which MPI takes in the arguments might be different. We will look at it later. I just want to put it in the alphabetical order. So you have block length, count, and stride. So what is block length? Block length is 2, right? Basically you have two values, right, in the old data type. That could be MPI int or MPI double or whatever. Then how much is the count? How many such blocks you want to send? You want to send 3 of them. And what is the stride? Stride is from here to here. So this is basically 1 2 3 4 is the stride, right? So stride is 4. Okay, so if you specify these, and then if you specify the starting memory address here, then MPI would automatically extract these values, and then from this kind of memory pattern in C, and then it will send these values. Okay, all right, we will see how this will be different in FORTRAN. If we were to even extract the same 3x2 cells out of 5x4, the memory pattern will come out to be different, because FORTRAN doesn't use a row major ordering. Okay, all right, so then how will we call this particular function? So we have this new function that is basically has a return type of int. You have MPI. Instead of type create struct, you have now type vector, okay, which will take in arguments of int count. So this is your number of block that we have, and then you have block length, int block length, okay, and then you have int stride. So as you can see, this is not in alphabetical order. This is count, block length, and stride, and then you have to give in, of course, the old data type and the new data type. So you have MPI data type, this is the old type, okay, and then you would give in a pointer or pass in the address of the new type. So it's a MPI data type star, new type pointer that you want to pass. Okay, now in if you are working in FORTRAN, well, we haven't discussed it yet, but then we can of course discuss the function call, right? That is basically MPI type vector, and then you would send in basically all these values: count, block length, right, stride, old type, new type, and then you would also send in this MPI error. Okay, semicolon is not required, even if you put FORTRAN would not compile. Okay, so so basically that is how we have done it. Now how will we how do we define which 3x2 block it has to extract? Because it could extract this one, or it could extract something else, right? If it could even extract the something like this instead of what we have said, right? This is also a 3x2 block or something else. Now to do that, you basically have to specify the address of the base value here, right? So this address you have to specify in the when you use the MPI send receive calls, right? That is where you would use this data type eventually, isn't it? So for that, you basically, let us say you would specify, if you want this block to be extracted, then you would specify this location. This is your x of, this is 0 1 0, this is 1 1. You would specify x of 1 1, and if you want to send let's say this 3x2 block, this one here, then you would specify x of 2 1, and so on. Okay, so that's what you would do. So that means what you would do is, in your call to MPI send, you would specify ampersand x of 1 1, and then you specify one of them, and then the new type that you have just allocated, and then all other arguments. Okay, so you are now sending one block, one type of new type data that starts with x of 1 1, and there is a 3x2 block that has a pattern that is defined in new type, and new type contains the required count, block length, and stride. Okay, so that is how things will work. and this is very useful when you try to do two-dimensional problems, where you have or three-dimensional problems where you have multi-dimensional arrays. Okay, and remember, this only works with continuous memory, so the arrays should be either statically allocated or I mean, should be only statically allocated in C, or they can be either statically allocated or using the allocatable function in the FORTRAN. Okay, fine. So let us now see how things will be different in FORTRAN, and if we want to basically represent the same memory in FORTRAN. So in FORTRAN, again, let us say we have a 4x4 array. So we have x of 4 comma 4. This basically goes from 1 to 4 here and 1 to 4. So what we have is x of 1 to 4 and then 1 to 4, and then just like C, I will represent rows in the horizontal direction and columns in the vertical direction. So you have x of 1 1, it starts with 1. Then as I go here, of course I have x2 1, x3 1, x4 1. This is basically the increasing in row, and then you have x1 2, right? I'm increasing the j index, and then x1 3, and then x1 4, and then all the way you fill up, and then you have x4 comma 4. Okay, so that's what we have. Now again, just like in C, the memory will be continuously allocated as a single block. You have 1 2 3 4 5 all the way to 16 elements. Now how this is done in FORTRAN is basically represented using a column measure ordering, right? Also known as co-lexicographic ordering. And then in that I would basically draw this matrix again, but then with these one-dimensional index that runs from 1 to 16 instead of these two-dimensional indices I and j. Okay, so if I do that, we would know the memory pattern. So instead of going in the row major order in the C, here FORTRAN uses column major order. So it goes from 1, it goes to second column, it goes to third column, and then fourth column. Okay, and then it comes back to the next row. So 5 6 7 8 9 10 11 12 13 14 15 16. Okay, so that's how it will be represented in FORTRAN. And then now if you were to kind of extract let's say again this particular 3x2 array or sub array out of this 5x4 array, let me again draw it. Okay, so I have this, okay, and then I want to have, let's say 1 2 3 4, and then we want to have columns. This is first column, second column, third column, and then fourth column. So we have 1 2 3 4 5 by 4, and then we want to extract let's say 3x2 out of this, right? So which 3x2? Okay, so this 3x2 only. Okay, we want to extract this 3x2. Okay, this is basically the same 3x2 that we have extracted in the C as well. Okay, all right. Then okay, fine. So we want to extract this 3x2, and then now before we do that, how is this represented in memory? So because it goes in column major order, I would draw 1 2 3 4 blocks, which would in turn contain 5 elements each. So we have first block, we have second block. I think this is too long, so I will redraw them again. 4 blocks with 5 elements each. So this is the first block, this is the second block, third block, the fourth block. Okay, and then I would like to put in 5 elements. So it's 1 2 3 4 5, 2 3 4 5. Okay, 1 2 3 4 5, 3 4 5. Okay, so and then so it goes in the FORTRAN goes in the row major column major order. So it goes this way. So the first block doesn't contain any elements, needs to be sent for the vector. Second one contains, and second one contains what? All the 3. So basically starts from, so leave the first one and the last one. So it basically contains this chunk here, and then the next one also contains a chunk here. So basically these 3 values. Then the last one would not contain anything. Okay, so basically we ended up with a different pattern, because this is now 2 contiguous blocks of 3 each instead of 3 contiguous blocks of 2 each. Okay, so let us see using the same alphabetical order thing. Let me use block length, count, and stride. So what will it be if you have to write it for FORTRAN? So what will be, oops, one block here. Okay, So what would be the block length, count, and then the stride? So the block length would be how much? So block length would be 3 here, right? This will be 3, and count would be 2, and then how much is stride? Stride is from here to here, so you have 1, 2, 3, 4, 5, right? So 3, 2, 5. And then earlier in C, to represent the same memory, in C for the same it was 2, 3, 4. Okay, see, this is kind of different, so you need to be careful when you put this, otherwise you end up sending different data and your programs would not work the way they are supposed to work. Okay, and then you would again send in, if you have to send in this data, this will be, because this is x11, x21, x12, x22, so you would send in x22. Okay, so MPI send in FORTRAN, you would say x221 and then the new type, everything, and then the MPI error. Okay, so that's what you would use in FORTRAN. I mean, this can be even all caps or lowercase, doesn't matter. Okay, so just like the type create structure, here also you need to commit the new data type before it is used. Okay, so you need to commit this before you can use the new data type. That needs to be done. Okay, so now let us take a quick example at where you may get these kind of patterns. So let us talk about, let's say we have a two-dimensional domain, and then you have basically drawn a grid, right? Just like in Jacobi or something, you're trying to solve this particular system. I think this is too many. Okay, these are supposed to be vertical lines. Okay, so they are somewhat vertical. Okay, and then let us say we basically have kind of partitioned this system in both an x and y direction, and then we you know, one particular process has to work with all these elements. Okay, all these elements belong to one process, and then when you, if you remember, we had these calls such as x of I minus 1. We know if you were dealing with phi, you in the discretization you have phi I minus 1j, phi I plus 1j, and then phi ij plus 1 and phi ij minus 1, right? So if you have to exchange, so these data, if you are at the boundaries, that means this has to come from the other process, right? For example, this data is what would be required when you are at the boundaries, and similarly this data would be required, and this doesn't belong to this particular process. Let's say this is process 0, process 1, process 2, process 3, something like this. Then this data would be actually on a different process, and that needs to be kind of sent. Oops, I want the same different color. And that needs to be sent to this process, right? Similarly, you know, this data might be relying on another process. So we need to send this data to process 0 at certain intervals, right? Such that it can make use of that and then calculate it. Now what you notice is that because the problem is 2D, although probably if you are lucky, one of them could be continuous data, the other one would not be continuous, right? Whether you take C or FORTRAN, you stick to one of the programming language. You take C, then one of them, depending on row major or column major, depending on, because it's a row major ordering, this will be, if this is continuous, this would basically come out to be will come out with a gap of these elements, right? Similarly, if you take FORTRAN, one of them could be continuous, right? This could be continuous, and then this could be not continuous. So you basically have to use both the continuous and the vector types depending on the patterns, and such patterns come when you try to solve 2D problems, and things get a lot more complicated when you do 3D, because in 3D you not only have a line like this, you basically have a surface, right, that you need to exchange. So essentially all the data on this particular surface needs to be exchanged. Similarly, all the data on this particular surface needs to be exchanged as well. Okay, so so it gets a little more complicated, but then once you figure it out for all of these, you can easily define your new you know, vector type, and then use that to save a lot of time in the exchanging the data elements one by one. Instead, you can just exchange all these in one go and save a lot of time. Okay, all right, so that is all I wanted to say regarding the MPI programming. We have performance analysis and performance evaluation and things like that, which we'll try to catch up in the next class, and then thereafter we'll move to numerical methods using MPI. Okay, of course there are several function calls that we are not covering all of them, but if time permits, we will try to cover them in the, or if required, in the numerical methods part of MPI. Okay, so for now I'm going to stop here. We will talk to you in the next lecture. Okay, thank you.